Okay, so let's take the case of simple harmonic motion of an object as shown by the yellow dot here. This is the equilibrium position of the object. It moves to the right all the way to the dotted line shown here, extreme position, and comes back, crosses the equilibrium position, moves to the left extreme, and comes back to the equilibrium position. This is one cycle, and it continues in a simple harmonic motion in this fashion. This distance is called the amplitude. So let's say we start measuring the displacement, velocity, acceleration of this object at time t equal to 0 in equilibrium position. This is one case. We can also start measuring for the same object when it's in motion, simple harmonic motion. We can start measuring here, then t equal to 0 is at the right extreme position. Let's take the case of t equal to 0 at equilibrium first. This displacement at this position, or the displacement for this object, can be written as a sine omega t. If we plug in t equal to 0 here, we see that sine 0 becomes 0 and displacement is 0, which matches with our position. That means it's starting at equilibrium position where displacement is 0. Let's call this equation 1. And if we differentiate displacement with respect to time, we get velocity. We know that. So velocity is differentiation of displacement or rate of change of displacement denoted by x dot. That is a differentiation of sine omega t is cos omega t, and again we have a omega t. If we differentiate, we get an extra omega here. This is equation 2, and acceleration is rate of change of velocity, so 2 times double differentiation of displacement x double dot. So if we differentiate equation 2 right hand side, cos omega t differentiation is minus sine omega t, and again for the omega t we get an omega there. So we get a stays there, we get sine omega t, and we get another omega and a minus sign. So it becomes minus omega square a sine omega t. This is equation 3. Let's take the case on the right hand side. We start t equal to 0 at the right extreme. So the displacement x is given by a cos omega t. If we plug in t equal to 0 here, we see that cos 0 is 1 and we get the value a, which is correct. From the equilibrium position, this distance is a, which is the amplitude, and we get that. So if we again look for velocity for this, when we start to measure at the right extreme, we differentiate displacement, we get cos omega t differentiated is minus sine omega t. So minus a omega sine omega t. So this is equation 1 here, this is equation 2 here, and then acceleration is given by double differentiation of displacement, which is rate of change of velocity is acceleration, and then we get for sine omega t differentiation is cos omega t, so we get minus a, the omega t differentiates to omega square cos omega t. So this is equation 3. So if we look at these two equations on the left hand side and right hand side for the acceleration, it's of the form a equals minus negative omega square x, because a sine omega t is nothing but x from equation 1 here. Similarly, on the right side, we get again a is negative omega square x, because a cos omega t is x from this equation. So this is the relationship between acceleration and displacement. We see that acceleration is always in the direction opposite to displacement. That's why the negative sign. Now looking at the signs here, another interesting thing to note that if we take this as positive direction and this as the negative direction, let's look at the left hand side first, where equilibrium position is t equal to 0. We see that it starts at the equilibrium position. So displacement can be positive or negative. We'll take it as positive. And then it starts moving to the right. So velocity is in the right direction, towards the right, and right hand side is positive for us. So velocity is positive. And Acceleration is always opposite to the direction of displacement. For the restoring force pulls the object this way back to equilibrium position. The force is in this direction negative, acceleration is also negative. So we get a plus plus minus, which is in line with the signs we get here. We get a plus here, we get a plus here, we already have a minus here. Same way for the position where t equal to 0, we start measuring at the extreme right. We see that at the extreme right, the displacement is already a positive, a plus x, because right direction is positive. From here it starts moving towards the left, so the velocity will be in the negative direction. And the restoring force is also pulling it back to equilibrium position. If force is in the negative direction, acceleration is also negative. So that's why we see a plus here. We already have a minus here and a minus here, which is in line with what directions we have found. Thank you.